Coming back, let us see. We will repeat what we did before. We have the continuous shape function. We'll talk about the continuous shape function. Then we'll talk about the discontinuous shape function. Okay? When we talk about the continuous shape function, remember we have phi 1 equal to 1 at the first node and 0 at the other nodes. And when we have phi 2, we have phi 2 equal 1 at the second node, and we have zeros at other nodes. When we have phi 3, it is equal 1 at the third node, and we have zeros at the other node. They should look like this. Okay? Okay. Now, let us see this. Now we have our fundamental solution, our integral equation. Our integral, it is integral over the element, the fundamental solution, times the density function. This could be u times t, or it could be t times u. Okay? So we want to change it. Instead of integral over the element, it will be integral from eta equal minus 1 to eta equal 2 plus 1, as I said now. The fundamental solution here, it will remain the same. And this density function, it will be phi times the nodal values. It will be phi times the nodal value times the Jacobian. So here we need to know each element of this. And here remember, this one is f of r. And this one is f of eta. Okay? And these numbers are constants. Okay? Let us see how can we do this. Bit by bit. Okay? Now, the Jacobian. You can, from any book of advanced calculus, you can see this Jacobian here. I will show it now from where it comes. The normal comes like this. Okay? Remember, remember when u of eta equal to phi times u, t of eta equals phi times t. Any x coordinate, this is x1 and this is x2. Any x coordinate, any y coordinate, it should be equal phi times x coordinate of the nodal values. The difference between here and here, this is very important. The phi here could be continuous or discontinuous. But here, the phi should be continuous, always continuous. Because when I interpolate to compute the value of the displacement, for example, I have element like this. If I want to compute the displacement here is based on the shape function of the discontinuous shape function. But if I want to interpolate any value of x1 or x2 or point here, it should be based on continuous shape function. Otherwise, I will have gaps for the element. So this phi should be different from this phi, these two phi. Here, always continuous. This is very, very important. Okay? When I want to compute for the Jacobian, the derivative of x with respect to eta and the derivative of y with respect to eta is straightforward. We can do it. The derivative of x with respect to eta is the derivative of the shape function times x, because these are constants. Okay? This will end up to a plus b, a or c eta plus d, the value of a and b and c and d, and we are going to give them now. So when you use a Jacobian, when you use a normal at any point, remember this minus here, this minus give you to remind us by the permutation symbol, but we leave it now. And this is our, instead of collocation point, we'll say it's source point, because some people, they claim this is a collocation point. So from the source point here, I'm going to integrate. So I will choose my Gauss points here, numerical integration. I have the Jacobian, I have the normal, I have r, I have r comma 1, I have r comma 2, I have r comma n. So I can carry out this integral straightforward. Compute the Jacobian, compute the values at Gauss points. So practically you compute the values at Gauss points. Here is very, very important point. Okay? When I come back here, I found this one is f of r. Okay? and I found here is f of eta. So it's very simple. I can write this one is sigma at Gauss point to the function f of r times phi at Gauss point times the Jacobian. Actually, this is the integral. Okay? At Gauss points, when you Gauss point in terms of eta, so phi is not a problem, j is not a problem. The question is how to compute f of r at Gauss points. The idea is very simple. Instead of computing the value of the fundamental solution in terms of eta, we can compute the x and y at eta. Here we have 4 Gauss points, for example. From these 4 Gauss points, we knew eta at Gauss points is given. So from eta, I can compute x1 and x2 at eta. When I have x1 and x2 at eta, so I knew the coordinate, the real coordinate x and y coordinate at this point. So instead of computing, this is a fundamental solution value between the pole point xp and yp and the point here, and your point, your integration point here. Okay. So instead of computing this in terms of eta, we'll compute it in terms of r. Okay, because we have this one, we have x and y here, and at the end of the day here we have x and y at this point direct. So we will be able to compute r, we are able to compute r comma 1, we are able to compute r comma 2. This is a trick. This is a trick. So actually, coming back here, instead of changing our fundamental solution to be function of xi or eta, so we will compute the x and y coordinate as the integration point. Then we'll compute the value of the fundamental solution at the eta point using r. Okay? Instead of computing everything to this, we'll compute direct in terms of r. I'm writing this idea. Here, as we see, remember, any integral between 1 and minus 1 equal to sigma over Gauss point, the value at Gauss point times the weight at Gauss point. For example, if we integrate from minus 1 to 1 eta squared times d eta equal to sigma over 4 points, the value of eta at Gauss points and the value of eta at Gauss points, the value of Gauss points are given and the weights are given. I gave it to us, to you in previous lecture or something like this. So the idea is very simple. The idea is very simple. I will jump to the last point. The idea is very, very simple. Instead of computing f of r, remember we have f of r and we have phi. We have phi here. Okay? Instead of computing this one in terms of eta, so we have integral minus 1 to 1 f of r, this is a fundamental solution, times phi of eta times the Jacobian of eta. So this one, it is sigma on Gauss points to f of r times the phi of eta, j of eta. So Gauss point is defined in terms of eta. For example, you have here, this is eta, it gives you 4 Gauss points, for example, at eta equal, say, minus 0.7, eta equal minus 0.2, and the same, eta equal 0.2, and eta equal 0.7. So we have 4 Gauss points. So we will substitute phi of eta, we knew it. The Jacobian of eta, we knew it. From where is the Jacobian of eta? We knew it. Here it is. This is the Jacobian of eta. The first derivative with respect to x eta, the first derivative with respect to eta of x and y coordinate is a function of eta. Okay? The main problem we have is the fundamental solution. We need to compute this fundamental solution between the integration points and the source point, xp and yp. So we need to compute this one. So instead of changing everything to eta, will it change eta here to x and y? Because we can compute x and y for the eta points. And from x and y here and x and y here, we can compute f of r. So this is the idea. This is the idea. The simple way it should change everything as I wrote here, to change everything f of r to r, to compute the value of the fundamental solution at the integration points in terms of the x and y coordinate. Okay,